Hi guys, it's me, Mr. Bertoch, your incredibly handsome science teacher. And in this video, we're going to talk about Newton's second law of motion. In another video, I talk about Isaac Newton and his laws of motion, his first law of motion, that is. In this video, I'm going to talk about his second law of motion, and then in another video, I'll talk about his third law of motion. So Isaac Newton was this amazing tastical guy who had an incredible ability to close his eyes and imagine the universe and figure out how things in the universe work, and to perform what we call thought experiments, which is simply using your imagination in order to do an experiment when you can't actually experiment on the thing in the real world. Isaac Newton had this profound and just amazing ability to imagine things, and he was able to use that imagination to develop a lot of human knowledge, to advance human knowledge quite remarkably. Among those is the laws of motion. And the first law of motion is that an object at rest will remain at rest, an object in motion will remain in motion unless acted upon by an outside force. He also figured out that we can actually calculate how much an object will accelerate when you push it, essentially. So, for example, if I have a really annoying little sister and I push her, I shove her because she's mean, I can use math to figure out how fast she will fly away from me. Or if I am a nicer brother and I don't shove my sister, but instead let's say, throw a bowling ball down the bowling ball lane, I can calculate how quickly it will accelerate, except that that's actually a complicated calculation because I have to deal with friction. So let's go into outer space. Let's say I go up into outer space where there is no friction, and I take a bowling ball and I throw it, not at my sister, just randomly out into space. I can calculate how quickly the bowling ball is going to accelerate. What does accelerate mean, by the way? Accelerate is just a fancy sciencey word that means speed up. If I am accelerating, I am speeding up. I mean, think about how incredible it is that Isaac Newton figured this out when he figured this math formula out when there was no way he could go up into space because he lived hundreds of years before rockets. And yet his formula is spot on accurate. So he figured out that the amount of acceleration of that bowling ball is equal to the force that I apply, the net force that I apply, divided by the mass. Okay, so force means like how hard I'm shoving it, right? How much force I'm applying to it. And mass, I talk about in another video, is the amount of atoms in an object. So if I take the force, the amount of force that I shove it, and I measure that force, and then I divide it by the amount of the amount of atoms, or the mass, I am going to get a number that is equal to how fast the object will accelerate. So this formula, the formula that I can use for acceleration would be acceleration. A is equal to F divided by M. A equals force divided by mass. Well, I can rearrange this formula, and we typically do when we're talking about the second law of motion, to be force equals mass times acceleration, F-ma. And you will remember that the rest of your life, F-ma. Force equals mass times acceleration. This is the typical standard way of writing the formula for Newton's second law. Newton's second law is simply stating that the more massive an object is, I mean, think through what this formula, because right now I'm just giving you a formula. And you're like, okay, but what does that mean? And when we are doing science, it's always more important that you can conceptualize what something means than that you can memorize a formula. So memorizing the formula is great, and you will remember this one. Force equals mass times acceleration, FMA. You'll remember that. But you also need to be able to conceptualize what that formula is saying. But this is logical. This makes sense. So you can envision it. You can do your own, like Isaac Newton, you can do your own thought experiment, and you can see this happening in your head, okay? Because you have enough experience to know how this works. So if I take a bowling ball, let's say it's like a small bowling ball, and it's not very massive. It's got some mass, but it's not very massive, and I shove it with a certain amount of force, you know that it's going to go forward and it's going to accelerate. If I take a much more massive, let's say it's like, I don't know, it's like the size of I'm trying to think of something that's like the size I'm imagining in my head that you would relate to. Let's say it's the size of a beanbag, like a big beanbag chair. Okay, so I take a bowling ball that's like the size of a softball, and I take or let's just stop calling it a bowling ball because these aren't sizes of bowling balls. I take a hard still ball the size of a softball, and I take a still ball the size of a beanbag chair, and I go into outer space, and I push one with each hand with the exact same amount of force. What's going to happen? Which one is going to accelerate faster? You know the answer. This is logical. The smaller one, the softball size one, is going to accelerate more quickly than the beanbag chair size still ball. And the reason is because all of those extra atoms, every atom that I am pushing, when I push both of those balls, every atom that I'm pushing is absorbing some of the force. And there are so many more atoms in the bigger ball that it is absorbing a lot more of the force than the smaller one. And so the bigger one isn't going to accelerate nearly as quickly as a smaller one. And so as time goes on, let's say I'm out in outer space and I shove them away, goodbye, and they go off in ahead of me. Well, one of them is going to travel much further, much more quickly than the other one because it accelerated more quickly. And it's always going to just continue to increase the difference between the two, getting further and further ahead more and more quickly because it's got a smaller mass. And this is logical. Okay, so when I write the formula, acceleration equals force divided by mass, what am I saying? I'm saying the force, the amount of force that I shove the object with is divided makes things smaller, right? Divided by the mass. So the mass is how big the object is. So the bigger the object, the more I'm going to make the number, I'm going to make it smaller. The force divided by the mass. So if I have the same force, but one side has more mass than the other, then that mass is going to divide. That's a bigger number I'm dividing into the force, so my acceleration is going to be smaller. I'm going to get a smaller amount of acceleration. So the math is just, the formula is simply a way of mathematically describing what makes sense conceptually in your mind, what happens when I shove objects. So this is Newton's second law of motion, which simply states that I can calculate how fast something's going to accelerate based on the force that I apply to it and how massive the object is. The more force, the harder I push it, the faster it's going to accelerate. But the more massive the object is, the slower it's going to accelerate. So both of those things come together to give me the acceleration. Again, if I take two objects and I put them side by side and they are the same size, okay, so now I have two objects of the exact same size and I shove them, one really hard and one softly, I'm going to get the same result, right? So if I shove one really hard and one softly, the one I shove harder is going to go further because the force is greater, even if the mass is equal. Okay, so we have to account for both of those variables. We have to account for how hard we're shoving the object, the force, and we have to account for how massive it is. And again, force increases the acceleration, mass reduces the acceleration. So force divided by mass gives us the total acceleration, but you can write it as A equals F divided by M, but usually we write it as F equals M times A, which is force equals mass times acceleration, which is F ma. And that is a way to remember it forever. F ma is Newton's second law of motion. Hi guys, thanks for watching my video. These rambling science videos where I go unscripted and just kind of barf up all the science knowledge out of my head are part of a series that go along with an online class that I teach, which you can sign up for if you go to handsomescienceteacher.com. I also have a whole bunch of free resources for homeschoolers. I have hundreds of articles on every topic that covers your entire science curriculum from 5th through 8th grade. I have online games and quizzes, all curated and written by this handsome guy, a science teacher with, well, three degrees, but 2 of them are in science. So it's targeted right to and directly to your science students. So sign up, subscribe to the channel, and I release lots of videos. Also, in addition to these ones, lots of little short videos that are like 2 minutes long that cover science topics. Those ones you don't get to see my handsome face, but they're still good videos and they're much more targeted, and those ones are scripted, so you don't have to hear me like you are right now going blah blah blah. The end. Subscribe. Thank you. Goodbye.